Recording is rolling. It is Tuesday, August 30th. So, you guys know I'm not going to see you guys tomorrow. You guys got to be set up at the sub. But I will be back on Thursday, and I will get you guys a take-home quiz on Thursday. Take-home quiz has been a pretty good format last couple of years. One thing let's do is have more class time for labs, sort of thing. And it's going to work out. So try that again. And then this Friday, I'm going to pick up you guys' homework, which is this page right here. You guys remember this page? Right. So actually, most of the day plan is to just do as many of these as I can do with you guys. Okay. Now there are also these conceptual questions on the other side. These are some really good questions too. I'm thinking probably Thursday. I think I want to do this with you guys because they're good questions. But is that okay? All right, you guys good so far? And so start a question. Actually, you start questions based on this scenario. Suppose you throw a ball straight upwards at 30 meters per second. Okay, goes up, goes back down. Okay. You guys know that gravity is pulling downwards at about 10 meters per second squared. Okay. So these three questions. What's the hang time of the ball? Say, what's the total time it's in the air from here to here? What's the maximum height that it goes up to? And also, what is the crash speed? Like how fast is it from down here? You guys a little time to solve those. It might be helpful possibly to reference these three kinematic formulas, which are on that green poster above that door. Okay, same thing right there. But there you go. There's a scenario. You guys can solve these before I start helping you, then that is a good sign that you know how this works. All right. Did anybody solve any of those three questions? Any of those three? Oh, yeah, what you getting?
I got 6 seconds.
6 seconds? Okay, you guys got 6 seconds for the hang time? Oh, yeah. Yeah, either of them ones or hang time?
I got the others too.
Yeah. What's the other ones?
Maximum height of 60 meters.
Yeah,
So,
not quite that tall, but
really?
yeah. But 6 seconds is the hang time. Okay, so let's get these one by one. And there's different approaches you could do. So here's what we do. I'll walk you guys through second by second. Is one way to do it. And then I'll break out those equations and show you guys like multiple ways to get to these answers. So if you throw it straight up at 30 meters per second, and you guys know that gravity is pulling down at 10 meters per second every passing second, how fast is the ball going after 1 second?
20 meters.
20 meters per second. And here it's how fast? 10 meters per second. And here it's how fast? 0 meters per second. Here it's how fast? 10 meters per second. 20 meters per second, and this would be downward, and 30 meters per second down, which actually answers the last question, doesn't it? But what is V crash? If you step through second by second, right? You guys know the velocity is changing vertically 10 meters per second every passing second, right? Towards the ground. Okay? So it's 30, 20, 10, 0, 10, 20, 30 meters per second. Okay. Now, what about so here. That could also answer the first question too, right? What's the hang time? And what's the answer? But you guys said 6 seconds, right? Because 1, 2, 3, 4, 5, 6. You guys see how my picture aligns with like take a picture every second, right? Okay. How about we break out these equations? Because you could have solved it with the equations. Say I want to get hang time, for example. Okay. Hang time, isn't that from the ground back to the ground? Okay. Guys, if you go from the ground to the ground, what is the displacement from the ground to the ground? 0. Yeah, right. This is just one approach that you could do, right? So remember, displacement is path independent. So all you care about is where you start, where you end. The ground back to the ground is 0. Here's what I'm trying to get at. If you want to answer the question like time and you know displacement, only one of these three kinematic equations deals with both time and displacement, and that's which one? The first one, yeah, it's the only one that has both the X and the T in it. See, the other two either have one or the other, but not both. Right? So I'm gonna pick that first one. Solve it this way. X equals B naught T plus half AT squared. Right? Then start plugging in numbers. You guys know from the ground back to the ground. You guys just told me this was 0 meters. Through this at 30 meters per second upward. Okay. Now, if I'm calling this number positive 30 meters per second, then down the line, you guys know that means the acceleration is going to be what? Positive or negative? Negative, because these two guys have opposite signs. If you throw it upwards, but gravity's pulling downwards, you have somebody has to be negative, right? Right. So we're trying to figure out what's the hang time. That was the first question, right? What's the hang time? Right, so pretend you don't know that the answer is 6 seconds. Right, so yeah, negative 10 meters per second squared for gravity. Right, and then T being squared. Right? According to the setup, which way did I define as the positive direction, up or down? Up. Right. Did I have to do that?
No.
No. You could have tagged the negative here and put the positive here. That would have been fine too. Yeah. Oh, okay. I see 3 terms. Hey, what can I divide all 3 terms by to simplify this really quickly? Okay, yeah, 10, true. But also T. Because otherwise it almost wants to be quadratic, doesn't it? Right. In fact, if this ball like landed on a hill over here or something, this would turn to like quadratic. Okay. But since this is 0, okay, just divide by T, divide by T, divide by T, right? So this T cancels. One of these cancels. 0 over anything is still 0. So this looks much simpler now. Just 0 meters per second is equal to 30 meters per second. Half 10 is 5, so minus 5. And that'd be meters per second squared. Keep track of the units, and then T. Okay. All right. That looks all right, right? Okay. 2 algebra steps. Add over 5T. Equals 30. Let's see. Meters per second squared, meters per second. And then the last algebra step is 2. 5 by 5. Second squared. T equals 30 over 5 is 6. Now the meters cancel. One of the seconds cancels, the other seconds flips back up on top. Seconds. There you go. Yeah, that's not the only way to solve that, but that's one way. Okay. 6-second hang time. Yay. 6-second hang time. Okay. You can use that to directly answer the third question. What is the crash speed of the ball? Okay. Because now that you know both throwing speed and the hang time, which equation could you plug into to get the crash speed? How about this one right here? Okay. If you're thinking of the third one, I think you could do that one too, but I'm going to use the second one. Okay. There's multiple ways to solve these, so if you do a different approach, then you do everything right, you should still get the correct answer. I'm going to do final velocity equals initial velocity plus acceleration times time. Okay. Now, if I'm solving for crash speed, that's like my final velocity, the crash. So I'm solving for. Remember, this guy was 30 meters per second upward, and gravity is 10 meters per second squared downward, so it's like negative 10 meters per second squared. Okay. And the hang time is 6 seconds. And this whole thing happened in 6 seconds. Right? Okay. So let's see, what's 10 times 6? 60. What's 30 minus 60? Negative 30. And the unit comes out to meters per second. So the crash speed is 30 meters per second. And then if you also include the direction to make that a velocity, it's 30 meters per second downward. That's what the negative sign means, right? Because I've defined up as positive, down as negative. Yeah. Okay. But remember, we kind of figured that out already too, because we're saying, well, if you follow the speed second by second, the speeds go 30, 20, 10, 0, 10, 20, 30 in terms of meters per second. So we knew that already, right? Okay. It's just a different way to get there. Okay. But you know what question we haven't answered yet? Is what is the maximum height of the ball? Okay. So has anybody figured that out by now? What's the maximum height? Okay. Now, just like these other questions, there's more than one way to get to the answer. But the maximum height, we don't care about going from here to here anymore. We care about something about including this point, right? Like all these kinematic equations deal with starting point, ending point. And if you want maximum height, you care about this as being one of your points, right? Okay. Now you can go two different ways with this. You could go, you guys see the total time it's in the air. You have to split it in half one way or another. Okay. You can either look at the first half of the story, it was thrown upwards and it reaches the maximum height. Or if you like, and I think this is intuitively a little easier, or at least my brain, is to look at the second half of the problem and say, well, if it started at maximum height, it had to fall some distance, and whatever distance it fell to get back to the ground would also represent maximum height. Is that true? So you can go either way with this, but you have to take this as one of your points. Okay? And at the very top, what special characteristic do you know about the very top that's going to let you plug numbers in? What is the velocity of the ball at the very top? 0. And that's going to let you know stuff, right? Let me make a little tax VV checklist. Sometimes that's helpful. Tax VV. Remember I told you guys if you didn't have how many of these, you can solve it? 3 things, right? So let's do this. Let's go initial velocity 30 meters per second, final velocity 0. So this guy could be 30 meters per second upward. This guy 0 meters per second. And that would tell you H max, right? If you're solving for H max, right? Hey, what's the third number you know? About gravity, right? Down 10 meters per second squared. Or since we're like overkilling this problem, you might have said, oh, well, I can clearly see time is going to be 3 seconds, but could have gone that way too. All right, so let's try this out. If you know 2 velocities at acceleration, you're looking for a displacement. What is the most direct way to solve this first, second, or third equation? Well, let's see. I don't have a time, right? Let's just make believe. Let's say you only know that. Yeah, go the third one, right? Okay. So let's go. Final velocity squared equals initial velocity squared plus 2ax. Okay. Right, so I know this guy is 0. I know this guy was 30 meters per second. Upward, square that. Plus 2 times gravity is negative 10 meters per second squared. And then x represents, well, h max, because that's the displacement. And here we go. Right. Okay. 30 squared is 900. Okay. So here. 0 equals 900 minus 20 H max. Okay. Add this over, divide by the coefficient. 20. All right. So if you throw a ball straight upwards at 30 meters per second, which by the way is about 67 miles an hour highway speed, the ball will rise to about 45 meters. You know what this sort of reminds me of? This goes back to a different approach to solve this. Where's No, the way I set up this equation is I was going from the throw point to the top point. But remember I said you could split this in half and look at the second half and just the ball falling, right? Okay. And if the ball takes 3 seconds to fall, now this is a different way of thinking of it. Okay. You guys remember go to the edge of a cliff, drop a ball? How far does the ball fall in 3 seconds? Guys remember that? 45 meters? It's the same answer, right? Is that? Let's do that approach too, like that one. So here's a simplified version. Okay. If you start from rest, this would be true. Let's pop it in. So 3 squared is 9, 9 times 5, 45, and then the units meters. Okay. There you go. Multiple ways to get there. All right. Everybody good so far? All right, so I think that's it's a pretty good warm up. Let's do as many problems as we can from this page. This page. Okay. Now yesterday I think we did the first 3 scenarios, right? Okay, so let's just keep on going. Next scenario: a ball is dropped off a cliff of given height on an alien planet. Alien planet. Which means maybe we don't know the gravity field. Right? It takes some given time for the ball to reach the ground, find the gravity field of the planet, and also the speed of the ball if it's crashing into the ground. Okay, so looks like I have the cliff height right here in meters. Somebody brought a stopwatch and says it takes this many seconds for the ball to reach the ground. And the fact that we're dropping the ball, like releasing it from rest, you know that initial velocity is 0 meters per second. Okay, I think I mentioned this before, but most physics textbooks you open up, they might give you this question, but they're not going to tell you 0 meters per second initial velocity explicitly, because if you see the word dropped, you should be able to figure that out, right? Okay, so we got these numbers. Okay. Now, if you look at my numbers, guys, a 24-meter tall cliff, and it takes 8 seconds to fall that distance. What if you were comparing to Earth, right? I'm just thinking about this problem, just putting it in a physics context, right? Compared to Earth. Guys, 24 meters to fall 24 meters on Earth, is that going to take more than or less than 8 seconds?
Yeah.
Less, a lot less, right? So if it did take 8 seconds, which it does on this mystery alien planet, then is the gravity field going to be really strong or really weak? Weak, yeah, really weak. So the answer has got to be less than 10 meters per second squared. Okay, you guys get that? Think about these kinds of mini questions as you're answering whatever target question you're trying to answer, because that might help you drive you along. Right, so you know x and t, and we need to solve for acceleration. What's the best approach? First, second, or third equation? You know x and t. First one, because that one has both the x and the t, right? See, if you pick one of the other ones, you guys notice we don't know a or vf. So there's a and there's vf. There's a, there's vf. There would be like 2 unknowns, right? You could do system of equations, but that would be overly complicated. So yeah, let's do the first one. First equation: x equals v naught t plus 1/2 at squared. I should get you guys a picture too. Cliff, an alien planet. Here's the height change. That's like height of the cliff. And maybe it's like your x, like h to the x. Okay. Drop a ball. Okay. So what is the crash speed? But before we get the crash speed, we gotta get the acceleration, the gravity field, and that's based on the fact that this whole thing was time. So t times. Okay. All right. So plug in these numbers here. I know the height of my cliff is 24 meters. 24 meters. The fact that you drop the ball, release it from rest, what happens to this term?
0.
Goes to 0, right? Let's go 0, 0, go away. So we're just down to 1/2 times. I'll say g for gravity field, which is tied to acceleration. And my paper says this whole thing happens in 8 seconds. Don't forget to square that. Okay. Let's see, 8 squared is 64, divided by 2 is 32. So 24 meters it falls. This happens 32 square seconds times g. Divide both sides by 32. I'm getting 0.75. And that'd be meters per second squared, which just describe an acceleration. So that looks pretty good. Okay. Remember before we even started plugging and chugging, you guys told me the gravity field should be really weak, and it is. It's less than 1/10 of Earth gravity. Okay, good.
Oh, my paper says that x is 22 and not 24.
Yeah. Okay. So everybody has different numbers on their paper. Right. So everybody has the same scenarios, just different numbers. Okay. Yeah. Good.
Why would you replace the G with the
Yeah, okay, so G is gravity field, which is a type of acceleration.
Okay.
So A could be any type of acceleration, it could be like if you're in a car slamming on the gas pedal. Or it could be free fall gravity, and then G is more specifically a type of
Okay.
acceleration. Yeah, so that's a great question too. Okay. Guys see that? But there's a follow-up here, and the follow-up is what's the crash speed? Okay, how fast is it landing down here? Okay, and now we have some options. What do you guys feel like, second or third? You really do either one, right? Okay, so yeah. Maybe just to overkill this problem, I'll do it both ways and show you guys it's the same answer either way. Okay. So final velocity could be initial velocity plus GT, right? Here's your G, 0.75 meters per second squared. And the time was still 8 seconds. See what that comes out to. Getting 6 meters per second is the crash speed, 6 meters per second. Okay. Or you could have done the third kinematic equation. Okay. Now, okay. Guys, the third one, if you drop it from rest, then V naught still 0, right? So this piece goes away. Okay. And I see one algebra step to get to the answer. Because if you want to extract VF, what do you do to both sides? Square root. Okay. So shouldn't VF just be the square root of 2AX? Okay. Or hey, could that be square root of 2GH? Okay. Have you guys seen that before this class? VF is the square root of 2GH as long as you're released from rest. Right? Yeah, this pops up all over the place in this class. Okay, and then it's really closely related to that third kinematic equation. So it's the square root of 2 times 0.75 times the height of my cliff was 24 meters. Okay, and I know what the answer is already, but what's the answer going to be on the screen? 6 meters per second, because this is just a different way to get to the crash speed. Okay. This way I did it through time. This way I'm about to do it here is through the height, the cliff height, but it needs to be the same. And it is. It's 6 meters per second. Okay. Okay, you guys right there? Okay, next one. So next scenario. A ball is thrown straight down at given initial velocity from a treehouse, given height off the ground. Find the time it takes to reach the ground and the speed that it hits the ground. Right, so if I'm looking at this table of values, looks like I know the gravity field, so we're on Earth, right, where tree houses are. Oh, I know how high the tree house is off the ground, so many meters. Okay, and I also know the throwing speed, so I do know how fast I'm throwing. Okay. Try to figure out how much time to reach the ground and also what's the crash speed. Okay. So number 9 and 10. Okay, so V naught goes straight down. And then this ball's hitting the ground. So hopefully be going faster than you threw it. Right? It's only picking up speed. It's falling down. Okay. And I did tell you guys the height of the treehouse from the ground. So maybe like X for general displacement. Okay, so you know acceleration, displacement, and initial velocity. We could get time and final velocity. What looks like a good place to start? First, second, or third? Like the third one? You know what? We can do the third one because we can answer the second question first. We can do that. Let's do that. Get the crash speed. So, well, yeah. So we'll start with number 10. Final velocity squared equals initial velocity squared plus 2ax. Okay. Now this one you can't quite simplify to just plain square root 2gh because you're throwing it, right? You're not releasing it. You're actually throwing it. Okay, so solve for this. I guess we could solve in terms of variables anyway because it's just one algebra step. It's still a square root, but it's V naught squared plus 2ax or 2gh. You could say 2ax or 2gh. It's the same idea, right? Okay. Look at some numbers. So my page says I threw this at 4 meters per second, be squared, plus 2, let's go 9.8 meters per second squared. And the height of my tree house is 9 meters. Giant square root right here. should give me the crash speed, crash velocity. Alright, so I'm getting this many meters per second. And I think that looks reasonable, right? Because here's what I'm thinking, if I chuck this thing straight down at 4 meters per second, and it's only picking up speed as it's falling, okay? Let's see, to fall, see 9 meters, that'd probably take about a second, maybe, right? About a second or so. I know if I dropped it, it would fall 5 meters in a second. So if I throw it down 9 meters, probably pretty close to a second. I know every second it's picking up 10 meters per second. 4 plus 10 is 14. Yeah, that looks reasonable, right? Speaking of time, that's the other thing we need to solve for. How much time? Okay. So what do you guys think to solve for time? Could you use the first one and do quadratic formula? You could. Would it be a lot easier to just use the second one? Yeah, I think so too. So number 9, final velocity equals initial velocity plus GT or AT. Okay. Hey, and solve number 10 first. We got final velocity is 13.9 meters per second. The throwing speed was 4 meters per second. Okay. Notice if I'm calling both of those numbers positive, which way am I defining as the positive direction, up or down? It's like down, right? I threw it down, it's crashing down, positive, positive, which means I'm going to plug in what for the gravity field? Positive or negative 10 meters per second squared? Gotta be positive 10. Because everything's just in the same direction, everything's just going down. So if everything's positive, makes it pretty easy, right? So subtract 4, divide by 10. So that's 2 algebra steps, right? Subtract the 4 and afterwards divide by this 10. And you get, well, I'm getting this many seconds. All right, you guys doing all right, too? Okay. While you guys are finishing that up, let me go ahead and check my work. You guys are trying your own numbers. Okay. So you know what equation we haven't used yet on this one is the first equation. I'm going to use that to check my answers because I know everything, right? I know everything already. Right? We were given the height of the treehouse above the ground. So I'm going to take the answers, like for t, well, I guess t in this case, right? Okay. Plug it into this first equation, and I'm going to confirm the height of the treehouse. So let's see if this works. So the throwing velocity was 4 meters per second. The time is 0.99 seconds plus 1/2 times, we've been using 9.8 meters per second squared on this page, and then times 0.99 seconds squared. Okay. Now, if this works, if all my answers have been okay, then I should be able to confirm the height of the treehouse was being 9 meters. That's what I got from the start, 9 meters. Let's see if I get 9 on my screen. 8.76. Guess that's close enough. That'd be closer than that. Wonder why. Oh, I know why. All right, because I realized it just makes the match my acceleration. Let me go back and solve for time again. Okay, I should have done 9.8 right here. I forgot I switched to 9.8 on this paper. Okay. The chat was 13 point. Okay. Actually, what's this more granularly? Square root of 4 squared plus 2 by 9.8 by 9. Okay, 13.87. Okay, minus 4 divided by 9.8 is what I should have said. Okay, 1.01 seconds. Let me switch this to 1.01 seconds. Didn't change it much, but okay. Now go back up here. So it's 4 times that time plus 1/2 times 9.8 times that time squared. Okay. So okay. Now let's see if I get what's it 9 meters. I should get 9 meters. Yeah, there it is. 9 on the dot. Right. Guys good? All right. Let's do. Okay. Let's do this very last scenario because we've done the entire left side of this paper at this point. Okay. But I know there's sort of a trick on this very last scenario, so I'll guide you guys through this one right now. Okay. A car brakes to a stop. It takes the car a given displacement and time to brake to stop. Find the acceleration of the car and the speed of the car just before braking. Okay. So get a picture. So 19 and 20. Car. Okay, so I don't know what the initial velocity of the car was, but the fact the car is braking to a stop, I do know final velocity is 0 meters per second. Okay. And we have the braking distance. X equals. Yeah, I'm gonna make up my own number just off the cuff here. Let's say 29 meters. Okay. And I also know how much time this whole process took. Okay. And again, I'll just make something off the cuff. Let's say this whole thing took 3 seconds. Okay, so now nobody has my number for sure. Everybody's got something different for me. All right, so what's tricky about this is that you cannot immediately solve for any variable using any one of these equations. Okay. The fact you know time, displacement, and final velocity. Now, time and displacement, you might say, hey, isn't that just the first equation, time and displacement? Okay. But notice you don't have either A or V naught. In fact, any equation you take, there's going to be two unknowns, okay, which makes it kind of tricky. So we can solve this with a system of equations. You guys remember a system of equations from algebra? Okay. So A and V naught. I guess I could pick any two of these and do system of equations. So maybe we'll pick the top two. Why not? You know, might know, but we'll see what happens. So let's go X 29 meters equals V naught we're solving for times T. We got 3 seconds. Plus 1/2 times A that we're solving for times the time that was given squared. Okay, so you guys see two unknowns right there. Okay. Now think ahead a little bit, because if the car is moving forward but braking to a stop, then is the acceleration going to be positive or negative? Negative. Yeah. So you get a positive value for V naught and a negative value for acceleration, just how it's naturally set up. Okay, that's one equation. I also need a separate equation. Let's go VF equals V naught plus AT. So that's 0 meters per second equals whatever V naught is plus acceleration, whatever that is, for 3 seconds. Okay. This right here is a system of equations. Okay. Now, everybody has different numbers than me, but you do need a system of equations, and that one should solve it. Okay. So different ways to solve systems of equations. One method is substitution. You guys remember substitution? Hey, can I take this bottom formula, maybe solve for one of these guys in terms of the other, and then substitute it into the top equation? Okay, can you do that? Okay. Here, how about this? How about is V naught equal to negative 3A? 3 seconds times A. Right? Isn't that true? Just subtract this over, point, just like that. Okay. And then you can take that and substitute it into the top one for V naught. So it'd be 29 meters is equal to, but instead of saying V naught, I'm going to use this entire bit of substitution. So negative 3A. So negative 3 seconds times A. My substitution, right? Times another 3 seconds. Plus 1/2 A 3 seconds squared. Right? Is that right? Okay. And see what's happened by this point. The fact that you substituted out the initial velocity means you have at this point one equation and one unknown. I see that? Okay. Now let me clean this up a bit. I'm going to drop the units. I kind of hate to do that, but just make it look a little cleaner. I got 29 equals negative 9A plus 3 squared is 9 divided by 2 is 4.5a. Okay. Is that all right? Okay. So while you guys catch up to that point, recap what I did so far. Okay. So we got, I picked two of those equations, set up a system of equations. So I got 2 equations and 2 unknowns. Okay. I'm using an algebra method of substitution. So I'm substituting out one variable in terms of another. Okay. So rearrange it, substitute. Now I have 1 equation, 1 unknown. And the way the process I chose is I'm solving for acceleration first. Okay. Guys good so far? All right, then if you have -9 of something and 4.5 of something, doesn't that create -4.5 of that thing? So you got 29, this would be meters, if I put the unit back in, -4.5, just be square seconds, then times a. Divide both sides by -4.5. I'm getting -6.4, and that'd be meters per second squared. That's actually a reasonable acceleration if you're hitting the brakes pretty hard. Right. Ooh, isn't that a little less than 1 Earth G? We're all in 1 Earth G right now, right? About 9.8 meters per second squared. This is what, about 2/3 of that? So the horizontal acceleration would be about 2/3 of an Earth gravity. Okay, so that's one of the answers. Now, the other thing we have to figure out is what is initial velocity. But you guys see we can get that very quickly by the substitution term. Okay, so go back to that, just -3 times the acceleration. So I'm taking this right here in brackets. Initial velocity must be -3 seconds multiplied by the acceleration, 0.4 meters per second squared. All right, and that's giving me 19.3. And the unit is meters per second. Hey, remember before I ever started plugging in chicken, I asked you guys what the signs should be for velocity and acceleration. We said, well, forward is positive, so it should get a positive initial velocity, but braking to a stop, you should get a negative acceleration. That's exactly how the numbers panned out too. Look at there. Right? You guys get that one? Right. You know what I want to do actually with these last about 10 minutes here is do some graphs with you guys. I want to do a set of graphs with this exact problem, and then one more set of graphs I can fit it in. Okay, so let's do a car braking to a stop. Car brakes to a stop. Okay. You guys know what 3 graphs I'm about to set up, right? X, V, and A, all versus T. So we got displacement versus time, velocity versus time, and acceleration versus time. Okay. So displacement in meters, time in seconds, velocity meters per second, time in seconds, acceleration meters per second squared, time in seconds. Okay, car brakes to a stop. Okay, now we've done the set of graphs for a few different scenarios. I usually start with the middle graph and then branch out from there. So let's do that. Okay. At time 0, the car is moving, right? We saw an initial velocity v naught. So we got that point on the board. But then if the car brakes to a stop, what does the rest of that graph look like? Is that going to be 0, right? So it hits 0 velocity after some time. Okay. And as long as there's uniform acceleration, then it'll just be a linear relationship like that, just straight down. Okay. Hey, what does acceleration versus time look like? Is that like down here? Okay. Let me go ahead and plug in my numbers for this scenario. I had an initial velocity of 19.3 meters per second. Have an acceleration of -6.4 meters per second squared. Like that. And what was the stopping time? The stopping time was 3 seconds, 3.0 seconds. Okay. I bet if you look at properties of graphs and compare these, but all the numbers should align, right? And how about displacement versus time? Okay. Now, this one takes some thinking. I'll give you guys at least 1 point. Let's say at time 0, we'll call it 0.0. Okay, so we get that point on the board. Okay. Once we got that point on the board, how does everything else look like? Yeah. All right, so Fred's saying it's gonna like hook down, sort of sort of like a spur type looking shape, right? Or actually, you know what? Sorry, I shouldn't say a spur. It should say like an upside down parabola, isn't it? It's an upside down parabola. Okay. And what point of the parabola is right here at the 3-second mark? The vertex. Okay. See how the car starts accumulating a lot of displacement per unit time, and then it's like getting less displacement per unit time. That's because it's slowing down. You guys see that? Okay. And let's see, guys, what should the area of this triangle represent under velocity versus time? What property of the car's motion? Check out the units. Guys, what is meters per second multiplied by seconds? Meters. Which has, okay, is that somehow describes the area of a shape. Hey, isn't that displacement of the car? Right. What is 1/2 base height for this triangle? Well, here's my numbers. Right. So 1/2 times height of the triangle times the base of the triangle. That's 1/2 base height, right? Okay. Let's see what displacement I get, which represents this right here. That is 29 meters. Well, it rounds to 28.95. That's basically 29 meters, right? Okay. 29 meters. That was exactly one of the given values. Look at there, right? And hey, I wonder what the slope of this line is. What does the slope represent? What physical property? The acceleration? Right. Let's see, rise over run, right? Let's see, it loses 19.3 meters per second, and it does that all in 3 seconds. Rise over run. Let's see what that is. See, negative 6.4 meters per second squared. Hey, that's what we got before for acceleration. That's the first thing we solved, right? Whole like substitution. You see how these physical properties are aligning with the math. Guys, good. All right. Any question about car braking to a stop? And I did want to fit in one more graph scenario. Okay, so this close out today. Okay, so now that you guys have seen some graphs, let's do you throw a ball downward from edge of cliff. Right, throw a ball downward. Okay. And let's call down positive direction. So down is the positive direction. Okay. Let's do X, V, and A all versus T. Down is positive. Okay. If down is positive, are these all going to be first quadrant graphs? It's all positive values, right? Okay. We'll call the top of the cliff 0.0, right? So X in meters, V meters per second, acceleration meters per second squared, time in seconds, time in seconds, time in seconds. Okay. Guys, if you throw a ball downwards, then at time 0, is it already moving when it's leaving your hand? Yes, it is. So shouldn't I throw a V naught like right here? Right, for the temperature? Okay. Now after that, what does the rest of this graph look like? Did you guys sit here? Trying to give you guys a moment to stay a step ahead of me. If you guys can answer these questions on your paper before I tell you what the answer is, that means you know what's going on. Would it be like this? Right? Doesn't the ball then pick up speed at a rate of gravity for some amount of time? Okay. And what is the slope of this line? 10 meters per second squared? Well, if you're on Earth, it is. The acceleration value. Okay, the slope of this is free fall G. It's like this is free fall G. Okay. Hey, do you guys think that the area of this trapezoid represents how far the ball has fallen, displacement? Okay. And if it's fallen for some general time t, then hey, what's the area of this here rectangle? Is that V naught times T? And what about the area of this triangle? We did this before. Isn't it like 1/2 AT squared or 1/2 GT squared? Okay, maybe just make this a G. Okay. Oh, and if you tag those two areas together, is that V naught T plus 1/2 GT squared? Hey, that's exactly what this says, right? So finally, just to round this out, sorry to do this a little fast, but this 1/2 GT squared is the area of that triangle. That's from before in your notes. So area of a triangle is that 1/2 base height. Base is T. Height change of that triangle is GT, right? Slope times base would be GT. 1/2 GT squared. Okay. We did that before. Okay. All right, so finally, last one to close out the class. What does X versus T look like? Is that still going to be a piece of a parabola? Yes, but is the vertex still going to be at the origin? Not quite, because it's already in motion when it's leaving your hand. That's to say that there's already a rate change of displacement when it's leaving your hand. And it'll dash a little line like that. And there's going to be a parabola that's flush to that. Starting to see how it kind of curves up. So it's a piece of a parabola, but it's kind of like flattened out. Okay. All right, you guys get that? All right. And that takes us to the end of class. If you guys have any questions, let me know. Got about 10 seconds to answer them.